Hello guys, this is Vishnu and today let us talk about applications of green chemistry and discuss started. So what exactly is green chemistry? Green chemistry is the design of chemical products and processes that reduce or eliminate the use of green generation of hazardous substances. Green chemistry applies across the life cycle of a chemical product including its design, manufacture, use and ultimate disposal. Disposal is a major problem on planet Earth nowadays. Green chemistry is also known as sustainable chemistry. Moving on, what is the purpose and the importance of green chemistry? And these points are as follows. So it prevents pollution at the molecular level. It is a philosophy that applies to all areas of chemistry, not a single discipline of chemistry. It's no matter what chemistry is included, then is the place where the green chemistry also plays a major role. Applies innovative scientific solutions to real-world environmental problems, and results in source reduction because it prevents the generation of pollution and reduces the negative impacts of chemical products and processes on the human health and the environment. Lessons and sometimes eliminates hazards from uh, existing products and processes. Designs chemical products and processes to reduce the intrinsic hazards. So these are the principles of green chemistry. Prevent waste, designing chemicals to prevent waste. I mean, less waste, high yield, and higher income. I mean, not income but higher profits. Maximize atom economy, design synthesis so that the final product contains a maximum portion of the starting materials. Waste few or no atoms. Design less hazardous chemical substances which are less toxic to the humans and also to the environment. Um, Design safer chemicals and products. Design chemical products that are fully effective yet have little or no toxicity. User safe solvents and reaction conditions, and increasing energy efficiency. And use renewable feedstocks. Use starting materials that are renewable rather than depletable, and avoid chemical derivatives. Avoid using blocking or protecting groups or any temporary modifications of possible derivatives. Use additional reagents and general ways. Using catalysts, not stoichiometric reagents. Catalysts will gradually increase the efficiency of the chemical processes um, and minimizes the waste. And design chemicals and products to degrade after use. Design chemicals products to break down to incontinuous substances after use so that they do not accumulate in the environment like pollution. Disposable problems will be occurring, and analyze in real time to prevent pollution, including processes real time monitoring and control during synthesis to minimize or eliminate the formation of byproducts, and also minimize the potential for accidents like design chemicals and their physical forms like solid. It may be a solid, liquid, or gas to minimize the potential for chemical accidents, including explosions, fires, and releasing into the environment. Moving on, these are a few applications of green chemistry, which are green solvents. The major applications of solvent in human activities is in paintings and coatings, which is up to 46% of usage, and smaller volume applications include cleaning, degreasing, adhesives, and in chemical synthesis. And a green solvent is a solvent that makes a product or process have the least environmental impact over its entire life cycle. And these are synthetic techniques. And I mean, what are synthetic techniques? What does it mean? So, novel or enhanced synthetic techniques can often provide improved environmental performance or enable better adherence to the principles of the green chemistry. So, hydrazine is a chemical which has been this is an example of preparing a hydrogen with the help of green chemistry. So, addressing principle two is the peroxide process for producing hydrogen. Without congenating salts, hydrazine is traditionally produced by the Allen-Wrestling's process for sodium hypochlorite. So, and this is a active ingredient in many bleaches, and ammonia is also been ammonia is also an byproduct. The net reaction produces one equivalent of sodium chloride for every equivalent of targeted product hydrazine. So, this is the reaction which undergoes, and the formation of hydrazine takes place. And moving on, this is another chemical 1,3 propanidiol, addressing principle 7, which is reducing the, I guess it's about reducing the waste, I mean, renewable, using the renewable waste, but not disposable, not degradable sources. So, is a green route to 1,3 propanediol, which is traditionally generated from petrochemical precursors, where petrochemicals are nothing but degradable things. It can be produced from renewable precursors via bioseparation of 1,3 propanediol using a genetically modified strain of E. coli. E. coli. This diol is used to make new polyesters for the manufacturing of carpets. And this is all about the 1,3 propanediol. Moving on, lactide. It's also a chemical, and a lactic acid is produced by fermenting corn and converted to lactide. And this the cyclic dimer ester of lactic acid used using an effective tin catalyzed cyclization. The L-lactic lactide enantiomer is isolated by distillation and polymerized in a melt to make a crystallizable polymer, which has some applications including textiles and apparel, uh, cutlery, and food packaging. Thank you.